Well, good afternoon, everyone. Hope everyone's enjoying the conference. So I'm going to take a bit of a shift on the solar side of it and look a bit more at hydrogen. All right, then. So my name is Strauss. I'm with Trinity Consultants. We do a wide variety of environmental health and safety consulting services. Today I'm going to be focusing a bit on our air permitting compliance projects that we've been doing with modifying existing combustion turbines in order to install hydrogen co-firing capabilities. So Trinity's had the opportunity to assist facilities across the country with permitting for Title V PSD power plant sources, and there's been a recent advancement in a lot of hydrogen technology in order to modify existing equipment and allow for them to then fire a new fuel in hydrogen or hydrogen natural gas blends. So from some of these permitting projects, it's going to provide some takeaways, some of the key challenges and hurdles that we come into, and then provide a bit of the background considerations from an environmental and air regulatory perspective facilities should be considering if they were wanting to implement such a project. So a bit more background on Trinity. As I mentioned, we do a wide range of EHS consulting services. I'd say for the most part, Trinity over the last 50 years has always been known for our air quality work, dispersion modeling, permitting, and compliance, but that's been expanding quite a lot to chemical, water quality, and haz waste reporting as well. As for myself, I'm based out of Trinity's Orlando, Florida location, graduated with a chemical engineering degree from the University of Florida, and then now transitioned over into more of essentially an environmental engineering and consulting role. During my time here with Trinity, I've had a lot of opportunities to work with permitting major power plant sources and assisting with general permitting compliance. But starting last year, we had the opportunity to work on a project with a power plant in Florida. They have a fleet of simple cycle combustion turbines, and they wanted to run a pilot project on one of them, essentially being able to install hydrogen and hydrogen natural gas fuel blending operations on a single turbine. And they did so in order to permit it up to 100% hydrogen fuel blends. We've seen it in Florida before, and I think the one other project that we weren't involved, I think they went up to about 10 to 15% hydrogen fuel blends. So this is quite a big jump in as far as the amount of hydrogen you can fire, what are those environmental implications, as it's quite a different fuel from what you usually see with natural gas, for example. So what's the deal with hydrogen retrofit projects? So what is a retrofit project? I mean, that's typically looked at as adding a new technology to an existing system. In our case, that's going to be taking an existing combustion turbine, adding a new technology in the form of hydrogen fuel firing capabilities. And then what is really driving these projects forward? I mean, the main one is simply that hydrogen is a carbon neutral fuel option. It's a alternative and considered renewable fuel in comparison to the common ones of natural gas or fuel oil, where it's not going to have carbon. So when combusted, there's no greenhouse gas emissions. I mean, the chart kind of shows it here that if you were to have a hydrogen natural gas fuel blend, the more you increase the hydrogen percentage, you can see that on the vertical axis, you're going to reduce your greenhouse gas emissions. It's clearly not a one-to-one ratio, but there's a clear benefit that using more hydrogen into a natural gas fuel blend or using pure hydrogen fuel is going to help with reducing your CO2 emissions. I think most current use of hydrogen, you'll see it in oil and gas, petroleum refineries. I think I've also seen it quite a bit with ammonia production for fertilizer manufacturing. But so now I think there's a turn to start using hydrogen in the power industry as well. And I would also like to note that hydrogen is not brand new to the power industry. You've seen it in some other fuels such as syngas, processed gas that have hydrogen-containing components, but the focus now is on a more low GHG fuel, carbon neutral, and the hydrogen's a really good option for that. So what are the main drivers? What's motivating these projects beyond just hydrogen's a carbon neutral fuel? I like to put it into two different buckets. We got regulatory requirements and then regulatory opportunities. For regulatory requirements, I like to look at the current and proposed federal regulations that are out there. One main example is the proposed rule replacement for the Affordable Clean Energy Rule. This rule affects both coal-fired plants, coal-fired units, new and existing combustion turbines, pretty much all your major EGUs. Specifically for existing combustion turbines, this focuses on a lot of the larger and more frequently operated turbines, and there are a lot of hydrogen co-firing requirements if you were to be subject to that proposed rule. In addition, for regulatory opportunities, this looks more at not a requirement for why you have to do a project, but what are the potential benefits of bringing in a renewable fuel, a fuel that does not produce GHG emissions. So some of those are incorporated net zero GHG goals. You see a lot nowadays with companies pledging to be net zero by 2050. And for a power plant perspective, hydrogen is a really good opportunity to move in the right direction towards that goal. ESG objectives are another one that fall into that category. And then also with hydrogen, it's another opportunity to increase your energy diversity at a power plant, and it's another form of on-site and nearby energy storage, which might differ from a lot of plants using natural gas via pipeline. Not always stored, some do, some don't. But hydrogen is a good option for having that on-site and really close nearby storage. So as I had mentioned, we had run into some permitting projects for getting these fired up and getting these permitted in Florida. And so I want to go through a few of the main challenges, as hydrogen is still relatively new to the power industry and utilities. So primary challenges, I mean, the main one is just that hydrogen is a new fuel. With current use mainly being in oil and gas and fertilizer and other smaller industries, power with using hydrogen, rules were not promulgated to consider hydrogen as a viable fuel source. So therefore, there's no explicit considerations for what defines a hydrogen fuel, what categories does it fall under, what are your testing, your emission standards, or what your reporting requirements are for a brand new fuel. Therefore, navigating both current and proposed federal regulations, there's very little precedent on that. And that kind of carries through the whole air permitting and regulatory side. So when it comes to quantifying emissions for, maybe not GHGs is no longer the concern, but there are trade-offs with NOx, for example, and the potential for increase in thermal NOx using hydrogen combustion. So with very little precedent on how to quantify emissions, how do you have to adjust your SEMS or your validity of using your DOS system for accommodating a new fuel, as well as what your compliance demonstration is, there's a lot of different considerations facilities have to think about for bringing on a new fuel option. And while not the main topic of this discussion, I want to bring up a few that are beyond the air regulatory scope. Some of those deal with like implementing the hydrogen generation method. I know there's been a few talks on that throughout this conference dealing with maybe using steam methane reforming, there's coal gasification, there's some renewable methods, nuclear methods as well. And a lot of those can play a role into your air permitting compliance and also drive forward what those regulatory opportunities and requirements you're trying to meet. For example, if your company has a net zero GHG goal and you were to go use a hydrogen generation method such as steam methane reforming, coal gasification, a lot of those generation methods end up inadvertently producing GHG emissions on their own. That almost is counterproductive in a sense to want to produce a carbon neutral fuel, but in order to do that, you're producing GHG methods in your generation method. So it's another thing to consider when it comes to your scope, as well as since it's all dealing with existing equipment, there should be a big focus on the current storage and transmission for transferring and storing the fuel once it's generated. A lot of facilities might not consider the different characteristics hydrogen has as a fuel compared to natural gas, fuel oil, LPG, even other hydrogen-containing fuels such as processed gas and syngas, as far as how those storage and transmission characteristics are going to be different, what's required, or the potential need for upgrades and replacements from an environmental perspective. And all those kind of lead into affecting your project scope, your design, the scheduling. And if you don't be accounting for the environmental impacts early on, that really can bite you in the butt later on. So going into what we found is the main challenges when we were doing air permitting projects for bringing on a hydrogen retrofit project. The main one is to first look at what the current federal regulatory applicability is. So most turbines are going to be regulated under the new source performance standards. And these contain, the main ones for this have NOx and SO2 emissions. And they set forth standards for they basically regulate NOx and SO2 emissions from the power industry, specifically combustion turbines. However, these are usually defined as being natural gas, which is the most common fuel used for turbines, and then pretty much all other fuels are non-natural gas fuels. It can also be looked at as being firing fuels like natural gas and then firing fuels other than natural gas. There's not really any set definition for hydrogen because it was not considered a viable fuel source back when the rules were made. Therefore, when you're looking at a natural gas or hydrogen fuel blend, or even firing a pure hydrogen fuel blend, there's really no guidance for what's the transition period. For example, if you have a 50-50 fuel blend of natural gas and hydrogen, and you're moving up and down, you change the hydrogen fuel blend, where does that transition from being considered a natural gas fuel into being a fuel other than natural gas, as they both have different sets of requirements. So therefore, when we're going through our permitting process, we have to really consider how do we determine what is defined as natural gas. There is set definitions in the rules and regulations, and we know hydrogen does not qualify under those rules. So where does that transition period come? And it comes with a lot of guidance and working with your state or local permitting authority to figure out the best way to characterize a different fuel blend or a pure hydrogen fuel and set forth what are your potential requirements and standards going to be. beyond just the new source performance standards, we also look at the national emission standards for hazardous air pollutants, or HAP. So there's potential HAP implications under some of the subparts for stationary combustion turbines. A lot of those deal with hydrogen does not contain the amount of carbon you would need, or it does not contain any carbon, so that wouldn't produce formaldehyde during combustion. Obviously, if you're using a hydrogen or natural gas fuel blend, there's still the chance to have an effect on formaldehyde concentration, which is usually one of the primary HAP concerns when it comes to potential emissions. And therefore, it can play a role if your facility, for example, you're working with an older turbine. Some of these may not have a SCR for NOx control, or they might not have an oxidation catalyst for carbon monoxide control. And if you have to be a major source of HAP, there's a set of alternative monitoring requirements for your facility as a major source of HAP and having a stationary combustion turbine. Hydrogen could potentially affect the way you petition for what your alternative monitoring standards are, but there's little precedent on that, so you have to consider the best way to approach that with a new fuel option. In addition to current regulations, there's also the proposed regulatory requirements. I mentioned it earlier in the slides about the proposed Affordable Clean Energy Rule replacement. So there's a set of requirements for just existing combustion turbines, which is the focus of retrofitting projects for hydrogen fuel firing. There's a set criteria, and that's for larger or over 300 megawatt turbines, and then they have to also be frequently operated, which is defined as having a capacity factor of over 50%. If a turbine were to meet these qualifications, there's then a sort of a two-step approach, or two different sets of requirements or best system of emissions reduction procedures they can follow. One deals with 90% use of carbon capture storage, which isn't the focus of this presentation, but that's one method of potentially complying with the proposed rule. But if finalized, the other set of hydrogen standards is kind of a two-step approach. The first would be 30% hydrogen co-firing by 2032 and 96% hydrogen co-firing by 2038. And this leads to a lot of questions for facilities, as hydrogen is not a prevalent fuel when it comes to the EGU service as a dispatchable fuel. So understanding how is your facility going to meet a 30% hydrogen co-firing requirement? In 15 or I guess 14 years now, how are you going to meet a 96% hydrogen co-firing requirement? What does the scale of that project look like? The amount of storage? How does the generation method play a role in all that? It can present a challenge not just from air permitting side, but just your overall physical project approach to what equipment are we going to need? What modifications are we going to need in order to potentially have to comply with some of these regulations? The next step in our permitting process often looks like, after we figure out the regulatory applicability or proposed changes what the retrofit project is, then evaluating emissions from hydrogen combustion. So the main thing with hydrogen compared to natural gas fuel is that hydrogen actually has a higher energy density on a mass basis, but there's a significant flip when you look at it on a volumetric energy density basis, which you can see in the chart on the right is that hydrogen is roughly 3 times lower of a volumetric energy density. So let's just say you needed X amount of energy from a pure natural gas fuel and a pure hydrogen fuel. You would essentially have to have 3 times the amount of volume of hydrogen in order to meet that same energy requirement, because it has a lower density. And these play into other roles, such as your pipeline infrastructure, to accommodate essentially a 3x increase, a 3x increase in the amount of flow of hydrogen you need. And that also factors into the storage, because obviously you're going to need a whole lot more hydrogen in order to achieve the same energy requirements that you would with the current natural gas fuel. So there's different trade-offs there with going from a natural gas to a hydrogen fuel combustion. Another one of those trade-offs is that high hydrogen fuel blends often lead to increases in thermal NOx. From a permitting perspective, this affects not just your regulatory applicability, but just your overall permitting approach in general, as depending on if you're a Title V, a major source facility, you might also have to consider PSD permitting requirements, which could often involve air dispersion modeling, and there's a lot of different intricacies when you're bringing in a brand new fuel and how best to approach it. When it does come to NOx, though, the one thing I did want to note is that NOx emission standards are usually provided on a ppm at 15% O2 corrected basis, and usually you're going to end up using some Part 75 equations, and these involve fuel-specific factors in order to convert to an hourly emission rate, a fuel-based emission rate, to understand on a pound per hour what's your NOx emission rate going to look like. When you're doing this for both hydrogen and natural gas, because you're using fuel-specific factors to do the conversion, it's not a 1-to-1 ratio, and therefore the values you get aren't going to be the same for both. And this also explains why on that graph I showed on one of my first slides that the curve of GHG reductions is not going to be 1-to-1 there. It's going to be slightly dropped back for hydrogen, because you're not getting the same comparison from these fuel-specific factors to get your GHG reduction rates or your NOx, even for your NOx emission rates. There's inconsistencies when doing conversions from a concentration to a hourly emission rate. And then one other small note I put was for PM 2.5 emissions. I'm not sure how many people were aware of that. I'm not sure if it's finalized by now, but I know there's the proposed lowering of the PM 2.5 NACs. With hydrogen not having as much carbon, there's a potential opportunity to lower PM 2.5 emissions, which could play a big deal in whether you're in attainment or non-attainment zones. Not much information or studies have been done on this, but it's something that the community with hydrogen firing has been looking more into as another solution beyond just GHG emissions to say, is this another way to lower our PM 2.5 emissions as well? For a few other considerations beyond it, like I mentioned, hydrogen generation method, the goal is to understand whether your method's going to produce GHG emissions. A lot of the processes we deal with were using electrolysis or a renewable method. Obviously, this would not involve the production of GHG emissions through it, but then there's questions on the energy intensity requirements. If you're using a set amount of electrolyzers to power up and generate your hydrogen, is there enough of that available? What's that commitment to resources necessary in order to bring enough energy to your facility and generate the hydrogen you need in the first place? Other ones deal with on-site hydrogen storage. I know there's been some other presentations about energy storage systems, but when it comes to hydrogen, from an environmental permitting perspective, there's risk management plan or RMP requirements. I think hydrogen has a 10,000 pound threshold quantity, and even for the trial projects we've been doing, they're getting very close to that 10,000 pound threshold quantity. And you can imagine for the trial projects we're doing, these are for like maybe a month of operation out of the year. If you're imagining large scale, you're more than likely going to exceed those limits. That's another set of environmental permitting you'd have to consider. And then bringing it back to the emission side, as I mentioned, there's these volumetric energy differences between hydrogen, natural gas. So this leads to questions on your infrastructure. You don't want hydrogen leaking out your existing pipelines. You'd like to know ahead of time as far as how to accommodate your resources and where the project focus has to be on. Do you need to upgrade your existing pipeline system? Do you need to add adequate storage? What other components of the turbine need to be modified in order to accommodate a new fuel? So these are all just other considerations beyond air. So then, after going through some of the challenges, we wanted to lay out some of the questions, I think, whether it's from a facility perspective, a corporate perspective, or environmental assistance perspective on what are the questions you should be thinking about when someone's considering implementing a hydrogen retrofit project. So the main ones deal with a lot of the regulatory applicability. What are your current regulations? What is if you have a turbine that's you're considering a project for, what are you currently subject to? How will the retrofit, if at all, affect that regulations and those requirements? The next looks at also proposed regulations, so that proposed age-rule replacement. If it's finalized, does your turbine fall under that applicability criteria? If it does, is hydrogen co-firing the best step forward in meeting those possible regulations? Others deal with other major permitting programs such as PSD implications. This mainly looks at NOx emissions, so if you're having a significant NOx emissions increase, that could require PSD permitting, air dispersion modeling, and all these different costs can easily start to add up on a scheduling and a project scale. Other ones, so compliance demonstration, emissions monitoring. There's very little precedent in the EUEC sector for what are the adjustments to your SEMs, to your data validity to figure out we're bringing in a new fuel, not just a new fuel, but potentially a new fuel blend between hydrogen and natural gas. What accommodations are we going to need to plan ahead of time for? Because it would be quite unfortunate to not think about that in advance. You install the equipment, you're starting commissioning, and then your data's out of whack, and you have to go scramble to figure out the best way to validate all that data. So then I just wanted to sum it up with a few of our main thoughts on that. So in addition to those questions, I think the main takeaways are usually that you want to be proactive on the environmental side for planning for these types of projects. I think the engineering is quite clearly immense in order to generate the hydrogen, store it, transfer it, what modifications are needed for your turbine in order to accommodate a new fuel. But overlooking the environmental considerations, especially on the air permitting side, can easily set back your project scope, your project design, and the scheduling, and cost as well, which is all very important to project managers in this industry. So then, like I said, the main ones dealing with understanding what are your current regulations and requirements for your turbines, how will these be affected by the project, proposed regulations, how will hydrogen co-firing factor into your potential future operations, next deals with understanding the best way to quantify emissions. So when it comes to quantifying emissions, it's often really important to understand how you're estimating NOx emissions, SO2, all these different types of emissions, because this can limit your overall project scope. For example, if you wanted to have about 1,000 hours of operation a year of hydrogen combustion, and you didn't really think too much about how to quantify emissions, you kind of just did it conservatively, worst case scenario, and just kind of put some numbers together, you might realize that after going through the air permitting, they're only going to give you 500 hours. And now you're looking at a deficit of, we want to have this much amount of operation, but we weren't smart about how we quantify emissions. And now our overall project scope for a trial project has been just slashed in half because we didn't think more about the best way to approach it on an air permitting basis. Other steps, like I said, planning ahead for compliance demonstration. There's not much precedent out there, but getting ahead on talking with your team, facilities on what's the best way to plan for potential SEMS changes, compliance demonstration. Are there going to be separate sorts of performance testing and reporting requirements? These ideas running through are the best ways to get ahead of schedule on those. And then also just considering areas outside of air. This could be the generation method, just economic and environmental impacts for whether it generates greenhouse gas emissions, energy intensity requirements, and then making sure that after you get everything permitted, you're constructing your hydrogen generation, you got your turbine modified, then making sure the existing pipeline can handle increased flow of hydrogen due to the volumetric differences, that you have the adequate storage for having this on-site fuel. So with that, I wanted to conclude the presentation. Thank you all. Leave it open for any questions. Yeah.
Do you recall the model server in Florida?
I can get it for you. I don't recall off the top of my head.
These were simple cycle?
These were simple cycle. They have a fleet of them at the facility they were at, and they had a few. I forgot exactly which one.
Are they peakers?
No, they have peakers, but these ones were not. They had a separate set that are like peakers at the facility, and these ones were just simple cycle, not peakers.
So they're utilized a little more.
I can't guarantee that's what's happening, but they're definitely used more than peaking units are.
I can see the business case for hydrogen in the long run for peakers.
Yes, yeah.
You mentioned the hydrogen supply issues.
Yes.
We're not sure we can get enough hydrogen for a baseload unit
Yes.
for decades. We just don't know the market will be there.
And that's the interesting thing. Like even with the proposed regulations, I mean, you saw how high some of these hydrogen co-firing percentages are. Obviously, these are for larger units, but I mean, even then, the supply requirements are immense, and there's not much shown to. I don't even recall anyone in the U.S. hitting 100% hydrogen as of yet, like being able to fire that off the top of my head. I've seen around 50, maybe less than that even. So to say in 15 years, you need to be hitting 96% all the time is a very.
I believe there's some aero derivatives
Okay.
that are hitting.
Okay. Thank you. I wasn't aware of that. Any other questions? All right. Well, thank you.